Hey there, my name is Brennan, and this is Physics Lab 1 for constant velocity. So the purpose of this lab is to understand systems with constant velocity, meaning no net force. And the way we're doing that is by conducting an experiment with constant velocity, and then trying to model that as accurately as possible. Well, with our understanding computationally. So this is going to be pretty much entirely reliant on Newton's second law of motion, and we can see here that, though, even with that simplicity, we were able to get some pretty convincing results of accurately modeling, this situation in the real world. So we're dealing just with Newton's second law and what you can derive from that. Since momentum, change in momentum over change in time is net force, and momentum is just mass times velocity. Change in momentum is, final velocity versus initial velocity. You can rearrange that into this formula here. No net force cancels out this whole second part. And so we're dealing to find position. We can simply take, average velocity being final velocity, final position minus initial position over change in time, rearrange that to solve for final position. And, that's the extent of the math and the physics that we're using here. Our system here is just going to be a rolled canister of hair cream, and surroundings are the desk that it's sitting on and everything else. We know that we have, constant velocity and no net force because the only forces that we're dealing with, the force of gravity and the normal force entirely opposing it, cancel out to zero, and everything else is constant. So as I said, initial conditions here, we're going to have this canister in motion. I have a little tracking dot on here so that in tracker we can find its position much more easily and accurately. And when, got a measuring stick, rolled it, started taping after it was already in motion and it finished speeding up, and, went and adjusted the axis and tracked that. And then when all of this data is plotted out, it's actually pretty high quality and convincing. We have an R² value here of 1, which in Excel is very good. They go out to like 4 decimal places normally. Because we have a constant slope here, which would be expected, for velocity. And this is just our average, speed per second. And so to try and model this using Newton's second law, in GlowScript, we have our code edited where our position vector was just the starting place, derived from tracker. Our ball of velocity, we had to take the position at the second frame minus position at the first frame and divide that by the change in time, which was 1/30th of a second. And then our delta t is that same amount of time because that's, the number of frames that we're dealing with. So while we have the amount of time that we gather data for, fnet is 0, which just leaves ball position as the position plus the vector that we have here times change in time, which is how much it's moving in a single frame, which is the exact situation that we were dealing with in our experiment. And if we look at what it outputs, this is what we would expect, where it's moving in a straight line at a constant speed, graphed on top of our observations from the experiment. We can see that they're actually really, really close here. We do have some discrepancy up here, but this is dealing with like fractions of a centimeter. And so that's actually pretty good for what we have here. Some of this error could be explained by the fact that we have air resistance, we have friction, although it was over a fairly short amount of time where that shouldn't matter too much. If our table was somewhat tilted, we could have been dealing with normal forces that weren't exactly canceling out gravity, or were in a different direction in the x-plane. And also there's just the fact that our extrapolated predicted velocity came from just the difference in position between frame 2 and frame 1, which that was dealing with like pixels amount of difference, which could make, when extrapolated out this far, a really large difference. So the fact that we see some amount of difference is to be expected both from error and from just the natural forces that our explanation doesn't take care of. If the axes were flipped, if we were in the negative x direction, we would still have the same results. The slope predicted would be steeper. We would just be going from 0 up here downwards. And then we know that while there are technically other forces that could be at play, well, having net zero forces, largely, things like the spin of the Earth or tilt or whatever, would be extremely negligible comparatively. And so we're really just having two main forces, the force of gravity downwards and the normal force counteracting it.